Good morning, Doctor. We are from SEEM 2133 Section 4, Group 6. Today, we will present the topic of separately excited DC motor. I'm Min Lu. Lin Qin and I will present the basic construction of separately excited DC motor. Separately excited DC motor has both stator and rotor. Stator is a stationary part of the machine and it contains the field winding that is used to produce the required magnetic field by DC excitation. Rotor is a rotating part of the machine which consists of armature windings. In separately excited DC motor, a separate supply is used for armature circuit and field circuit. From the torque equation of motor, the torque can be changed by changing the field flux and armature current. That's all from me. Lin Qin will continue the presentation. Thank you.
Hi, I'm Lin Qin and I will continue with the construction. As you can see, there are two coils separated. The field coil is powered by a DC voltage source and the DC voltage source is used to induce the field coil, while the armature voltage source might be varied, but it is independent of the field voltage supply. Thus, those coils are electrically separated. That's why it is called as the separated excited DC motor. The DC motor is used to provide the feel of an adjustable speed controller, but that might have some drawback like the commutator will cause the sliding friction, which will consume higher power, and we need to change the brushes frequently because of this. AC motor can overcome this kind of problem, but it is more expensive. That's why the DC motor is still the most applicable options in nowadays. Next, we will look at the operations.
On separately excited DC motor, we can find two circuits. On the left side, we can see a circuit where field winding is present. This circuit helps to create the electromagnetic field which excites the DC motor, which is present on the right side of the circuit. So this electromagnetic field excites this DC motor, and the armature is bounded by two brushes, this one and this one, and these two brushes helps the armature to spin.
This is a dot split curve of separately excited DC motor, and we have these two equations, and equation IA equal to TEM over KT prime VF. If we rearrange the equation, we can get the equation omega m equal to A minus B TEM. So if we increase the torque, the omega m will be decreased, and this graph shows the negative gradient. So for the speed control of DC motor, if we use the armature voltage control, it operates at a speed lower than the base speed, and it has a high efficiency and good transient response. And the remark is it has a constant torque. For the field flux control, it operates at a speed larger than the base speed. It can speed up to 2 times of the rated speed, and it has a constant power. For the armature resistance control, we didn't use it as it wastes power. So for the torque speed curve of separately excited DC motor, we need to refer to these equations. So for the armature voltage control, it has a constant torque. So if you use the larger VA, it will have a larger omega m. So for the field flux control, if you use the larger V, it will have a more flat gradient. So for the armature resistance control, if you increase the RA, it will have a more steeper gradient.
Hi, I'm Xing Shen. Rosie and I will explain about the application of separately excited DC motor. First, the separated excited DC motor can be an excitation source for the large alternator in power generation station. The large alternator require DC excitation to produce a constant magnetic field. Since the separately excited motor can produce a wide range of voltage, it can be used to produce the DC supply that excited the winding in the large alternator.
Besides, separately excited motor also can be applied as automotive traction motor. Since the separately excited DC motor has the fourth quadrant operation and regenerative braking system, the system makes this type of motor is suitable to react with the quick braking system. So this is a little bit about the separately excited DC motor. Thank you for listening.